Good morning. Today in this session we are going to discuss the constructional features and the characteristics of a power MOSFET. So what is a power MOSFET? A power MOSFET is a switching device that combines the field effect concept and the MOS technology. It has three terminals: drain, source and gate. So the figure shows the circuit symbol of the power MOSFET. Here the arrow indicates the direction of electron flow. Now a MOSFET is a unipolar device, that is its operation depends only on the majority carrier. Also, unlike a BJT, a power MOSFET is a voltage controlled device, whereas a BJT is a current controlled device. Now generally there are two types of MOSFET, that is N-channel enhancement MOSFET and a P-channel enhancement MOSFET, in which the N-channel enhancement MOSFET is the most commonly used one due to the high mobility of the electrons. Now let's move on to the constructional features of a simple planar MOSFET. So a simplified structure of N-channel planar MOSFET of low power rating is shown. So on a P substrate, two heavily doped N+ regions are diffused. Now an insulating layer of silicon dioxide is grown on the surface. Now this insulating layer is etched in order to embed two metallic metallic source and drain terminals. Here note that the N+ region make contact with this source and drain terminals. A layer of metal is also deposited on this silicon dioxide layer so as to form the gate of the MOSFET in between the source and drain terminals. Now let's go into the details of the principle of operation of a simple planar MOSFET. So in this figure, assume that the gate is open, that is, no supply is given across the gate and source terminals. Okay. So then the junction between the N+ region below the drain, that is this N+ region, and the P substrate is reverse biased by the input voltage VDD. Hence, no current flows from the drain to source and the load, since this junction is reverse biased. Okay. So now when the gate when the gate is made positive with respect to the source, an electric field is established as shown in this figure. So here this indicates the electric field. So eventually induced negative charges in P substrate. So the induced negative charges in the P substrate below silicon dioxide layer is formed, thus causing the P layer below the gate to become an induced N layer. So a portion of this P substrate below this gate terminal becomes an induced N layer. Hence, these negative charges called electrons form N channel between the two N+ regions. Okay, so this portion becomes NN channel. Hence, there is a continuity in this these N that is N regions. So there are two N+ regions, and in between the MOSFET P region, now it has become NN channel. Hence, now the current can flow from the drain to source as shown by this arrow. So as shown by the arrow. So here the arrow indicates the direction of current. And now if VGS is made more positive, induced N channel becomes more deep. So this induced N channel becomes more deep, and therefore more current flows from the drain to source. So this shows that the drain current ID is enhanced by the gradual increment of VGS. Hence the name, that is this MOSFET is termed as an enhancement MOSFET. So next is the constructional details of high power MOSFET. So the figure shows a planar diffuse MOS structure for N channel, which is quite common for power MOSFET. Now on the N plus substrate, high resistivity N minus layer is epitaxially ground. Now the thickness of this N minus layer determines the voltage blocking capability of the device. Okay, that is, the voltage blocking capability of this device is determined by the thickness of this N minus layer. Now on the other side of the N plus substrate, that is this part, on the other side of this N plus substrate, a metal layer is deposited to form the drain terminal. Here this shows the drain terminal. Now P regions are diffused in the epitaxially ground N minus layer. Further, N plus regions are diffused in P region as shown. So as before, silicon dioxide layer is added, which is then etched so as to fit metallic source and gate terminal. So now in this figure, when the gate circuit voltage is 0 and VDD is present, then N minus P junction are reverse biased and no current flows from drain to source. Now when gate terminal is made positive with respect to source, an electric field is established and electrons form N channel in the P minus region. That is P region here. So these two. So a current from drain to source, from drain to source flows, or it is established as indicated by the arrow. So this is the direction of current path. So with the gate voltage increased, the current ID also increases. So now let's discuss the power MOSFET characteristics. So first of all, let's see the static characteristics of a power MOSFET. So the static characteristics include transfer characteristics and the output characteristics. So first of all, let's see the transfer characteristics. So the figure shows the basic circuit diagram for N-channel P MOSFET, that is power MOSFET, where voltages and currents are indicated. So here the source terminal is taken as the common terminal between the input and output of the MOSFET. So the transfer characteristics. The transfer characteristics is the graph showing variation of drain current ID as a function of gate source voltage VGS. So a typical transfer characteristic shown in the figure. Here is threshold voltage VGST. So the threshold voltage VGST is the minimum positive voltage between the gate and source to indicate the to induce the N channel. So thus, for threshold voltage below VGST, the device is in off state. So the magnitude of VGST is of the order of 2 to 3 volts. Okay. So next is the output characteristics. So let's see the output characteristics. The output characteristics of a power MOSFET as shown in the figure. it indicates the variation of drain current ID as a function of drain source voltage VDS with gate source voltage VGS as parameters. So from the figure, it can be seen that for low values of VDS, the graph between IDS and VDS is almost linear. This indicates a constant value of on resistance RDS, which is equal to VDS by ID. So for a given VGS, that is gate source voltage, if the drain source voltage is increased, the output characteristic is relatively flat, indicating that the drain current is nearly constant. So a load line intersects the output characteristics at the points A and B. Here A indicates fully on condition and the point B indicates fully off state. Now in the ohmic region, the MOSFET acts like a closed switch, and in the active region, the MOSFET acts as an amplifier, and now in the cutoff region, the MOSFET acts like a open switch, just like in a BJT. Now this point is the drain source breakdown voltage. So thank you.